So on number 1 we have y prime plus y equals xy to the 2/3. You're working on that one, Ben?
Yes.
Okay. If I mute him, it doesn't mute my recording, does it? Okay.
Thanks.
So yeah, so we can see that this is already in the standard form. So this is already in the standard form as Bernoulli's equation that I explained above.
Right.
So we can introduce that substitution onto the differential equation. So go ahead and try it, and I'll do it alongside with you. Okay, so we're going to be using Bernoulli's. So we're going to say z equals y to the 1 minus n. In this case, n is 2/3, q is x, and p is 1. So that means z will equals y to the 1 minus 2/3. That means z3 equals y to the 1/3. And since we're going to replace this by y prime, we're going to differentiate. So dz over dx has to equal 1/3 y. So the derivative, subtract 1 minus 2/3 times dy over dx. Which means if I solve this for dy over dx, I will get 3y 2/3 dz over dx. I divided both sides by 1/3 y to the negative 2/3. I brought the y to the negative 2/3 upwards to the numerator. And I will plug this back into the differential equation. So dy over dx. So what I'm trying to do is I'm trying to do a substitution to go from y dependence to z dependence. So I can turn the differential equation into z and x instead of y and x. Now I could turn everything around the first step and solve for everything in terms of z, or I can save lots of algebra by just leaving y to the 2/3 where it is, and on the third step the y's will cancel out, as you will soon see. So dy over dx, I will plug in what I have. So we will have 3y to the 2/3 dz over dx plus y. I will leave y as y for the time being, equals x. Now y to the 2/3, let me leave it as y to the 2/3, and then I will divide this entire differential equation by 3y to the 2/3. So divide everything by 3y to the 2/3. And if I do that on the first term, this guy will cancel out and I get dz over dx. And if I divide y divided by 3y to the 2/3 equals x, the y to the 2/3 will cancel out and I will have x over 3. And the reason, okay, and then the middle one will become 1/3 y to the 1 divided by y to the 2/3 will become y to the 1/3 dz over dx stays the same, and this is 1/3 x stays the same. And the reason I did that is because, as you can see here, y to the 1/3 is just z. So I will remove y to the 1/3 and I will plug in z for it. So this will become dz over dx plus 1/3 z equals 1/3 x. And now this differential equation is first order z as a function of x, and I can solve this using the standard methods. Now this is a non-separable differential equation, so what I'll do is I work it out using the integrating factor method. And so the integrating factor method, what I'll do is I'll multiply it by an integrating factor mu. So I will call mu our integrating factor, to turn it, because this is a non-separable differential equation, by doing that I can turn it into a separable differential equation that I can solve easily. So mu dz over dx plus 1/3 mu z equals 1/3 x u. And what I'll do is I'll reverse this using the product rule, so I will say that this is d over dx of z mu. Let's label this A, equation A. I'll come back to it. Now if I actually apply, the reason I did that will be more clear as I perform this step now. If I do the product rule on z mu, then I will get dz over dx mu plus z d mu over dx is equal to 1/3 mu x, or x mu. Now if I compare this equation here with this equation, we can see that the first term is the same, the last term is the same, which means that the middle term has to be the same. But in the middle term, the z is the same thing as the z, which means 1/3 mu has to equal d mu over dx, which means this term here has to equal this in red, in the red squared. And this would enable me to find the integrating factor. So d mu over dx has to equal 1/3 mu. And now this is an easy differential equation. I can solve for the integrating factor, separate, so I have d mu over mu, divide both sides by mu, multiply both sides by dx, 1/3 dx. And now what I can do is I can integrate both sides. D mu over mu is mu, dx is x. Integral of d mu over mu is ln mu. The integral of dx is x, which means mu equals e to the x over 3. And now I can plug this back into equation A, which is this right here, and I can integrate both sides and separate them and solve for z. And once I have z, I know that y and z are related by my substitution that I started with at the beginning of the problem, so from there I could solve for y. Okay, so if I plug this back into equation A, I would get d over dx z mu z e to the x over 3 is equal to 1/3 x e to the x over 3. If I multiply both sides by dx, So I would get d z e to the x over 3 equals 1/3 x e to the x over 3. I can now integrate both sides of this, so I can put an integral here and an integral here, and I have my dx here. Now, fundamental theorem of calculus says the integral of a derivative is just the function itself. That's why this is convenient. I can easily solve for this. And the right hand side, of course, is integration by parts, x e to the x over 3. So by parts, let me drag this down a little bit. And if I call, so this is integration by parts, I will call u to be x and dv to be e to the x over 3, which means du will equal to 1 dx, and v, the integral of e to the x 3, is the same, divided by the chain rule, which is 1/3. And of course, integration by parts says that the integral of u dv equals uv minus integral of v du. And so now I can plug this here, give it a little bit space here. So 1/3, and I'll start the integration by part answer here. So I will plug in on the right hand side uv. uv is just x times e to the x over 3 divided by 1/3 is the same thing as 3 e to the x over 3 minus the integral of v du. So there's a 3 here because we're dividing by 1/3. I can put it outside because it's a constant. E to the x over 3, and du, which is this, is just dx. And continuing on, z e to the x over 3 is equal to 1/3 3x e to the x over 3 minus 3 integral of e to the x over 3. We've already done it above here when we did by parts. E to the x over 3, and instead of dividing by 1/3, I can just multiply by 3. I can bring the 1/3 in, so this 3 would cancel that 3. I would get e x over 3 minus 3, because 1/3 cancels 1/3, and we have a 3 remaining. And to solve for z, I can divide now both sides by x over 3. So if I divide here by x over 3, here by ex over 3, ex over 3 oh, we also have, wait, I forgot the plus c here. So plus c, so if I divide by ex over 3, and then on this plus c I also divide by ex over 3, these guys cancel out, they cancel out, they cancel out, and my final answer would be z is equal to x minus 3 plus c. I can pull e to the x over 3 up there, so this would be my z. So we're almost there. I know from the substitution I invoked at the very beginning that z is y to the 1/3, so so this is equal to y to the 1/3 equals this, because z is equal to y to the 1/3. This is the substitution I started with, and if I just cube both sides so I can solve for y, I would get y equal to x minus 3 plus c e to the x over 3, the whole thing cubed. So this concludes this problem, solving the differential equation using Bernoulli's substitution, Bernoulli's equation to do the substitution, then using the integrating factor method, through which we used integration by parts to solve for z, and then from there find the general solution for the differential equation, which is y.